Mathematics is a language of conceptual relationships. It is fluid, creative, and highly interconnected. But the way it's widely taught strips away that architecture, replacing it with a rigid set of memorized rules. This traditional approach to instruction operates on a two-dimensional design model. The horizontal axis represents factual content, specific numbers and formulas. The vertical axis represents procedural skills and step-by-step algorithms. Plot a student's learning here, and you get an intersection of fact and skill. But rotating our perspective reveals the entire space is flat, zero depth. A student might master both the x and y axes, achieving perfect procedural fluency on a test, yet their mathematical knowledge remains compartmentalized and disconnected from broader meaning. The central failure of this two-dimensional model is the assumption that if a student repeats a procedural skill enough times, a deep conceptual understanding will emerge as a byproduct. Because the assumption is false, students are left holding isolated pockets of knowledge rather than a cohesive framework. When knowledge is isolated, it cannot be transferred. Students encounter a wall the moment a real-world problem deviates from the exact formatting of their textbook. Success in a process-heavy curriculum depends on a fragile link of rote memory. If a student forgets one step or misinterprets a sign, the entire process collapses without any conceptual safety net to catch them, a dynamic that fuels widespread math anxiety. To develop true mathematical intellect and reduce that anxiety, instruction must transition to a three-dimensional model that forces explicit conceptual connections. Moving past the flat model requires a different blueprint for organizing curriculum, the three-dimensional design model. To build it, we take that flat plane of facts and skills and pull it into a volume by introducing a third axis. This new z-axis represents disciplinary concepts, generalizations, and principles. Implementing this dimension does not mean sacrificing the necessity of the x and y axes. The factual content and the procedural mechanics remain essential, but rather than treating those facts and skills as the final destination, the 3D model frames them within overarching big ideas. Operating in this 3D space requires synergistic thinking. Synergistic thinking happens when a student stops memorizing in isolation and starts processing facts in active concert with foundational principles. How does a teacher actually engineer this kind of thinking in a middle or high school classroom? The specific mechanism that makes this possible is inductive teaching. Inductive learning begins on the factual floor of our model. You anchor the lesson by giving students specific, structured examples to investigate. Using guided inquiry, students analyze those examples to find patterns. They move upward along the z-axis as they draw deliberate connections between the specific examples. The culmination of this upward movement is the formation of a broad mathematical generalization at the top of the axis. Students must have the space to independently construct these generalizations. Deriving the rule creates ownership, while being handed the rule creates dependency. Comparing the traditional instructional workflow against the new concept-based workflow reveals a sharp contrast in classroom dynamics. The traditional flow follows a linear path. You input facts, drill procedures, and assume a concept has been understood. The concept-based flow follows a dynamic loop. You input facts, facilitate guided inquiry, help students build a generalization, and then test that generalization through conceptual transfer. This shift redefines the educator as a deliberate engineer of inquiry, focusing on the specific structures that allow students to arrive at their own discoveries. This approach requires rigorous pre-planning. Curriculum design now demands unit webs and carefully crafted generalizations to map the inductive journey before students ever enter the room. Instructional coaches often ask how concept-based teaching fits within strictly mandated state or international standards. The 3D model is entirely agnostic to specific standards. It does not require abandoning a prescribed syllabus. You can view the 3D architecture as a flexible overlay that sits on top of any existing curriculum, whether it's Common Core, GCSEs, or the International Baccalaureate. This same logic applies to technology, including the influx of graphing software and educational apps in modern classrooms. Digitizing 2D rote practice does not improve learning outcomes. The specific tool matters less than how it is used to support the curriculum goals. Technology is effective only when it is explicitly deployed to enhance exploration along the z-axis, using its processing power to accelerate the inquiry process. Modern mathematics education reform pursues two goals: intellectual transferability and deep emotional engagement. Navigating the Z-axis fosters a growth mindset. Framing mistakes as part of the creative inquiry process makes the classroom a space of exploration, not fear. True conceptual understanding prepares students to solve complex, unforeseen problems in an unpredictable, dynamic world. This intellectual empowerment replaces the rigidity and fear generated by the old, flat model of instruction. Reconstructing curricula as a 3D architecture resolves math anxiety, unlocks synergistic thinking, and ensures lifelong mathematical literacy.